Okay, so let's talk about the Dirac field that we started in the last class. In the Schrodinger picture, psi of x vector uh, is written, so that's a certain time we choose and we take a snapshot of the space. So psi of x is to be written is d3p by 2 pi cube 1 by square root of twice ep sum over alpha of a p alpha u alpha e, the u spinner, and then exponential I p dot x, okay, plus b p alpha dagger v alpha p exponential I p dot x. So this is the Schrodinger picture. X is there and t, some reference time is chosen, same as in the scalar field. And when we move from here to the Heisenberg picture, so this is Schrodinger picture. Now let's change the color for the Heisenberg picture, and I will have psi of x. So this is full x here. This is just the time evolution of this guy, and time evolution is done through the free Hamiltonian, which we yet to compute. But let's just say, we can confirm it later also, d3 p by 2 pi q 1 by square root of twice ep sum over alpha, everything remains roughly same, p ap alpha u alpha p exponential minus I p dot x. Note that I'm not writing the vector sign over here because it's a 4 vector product, plus b p alpha dagger v alpha p exponential, I'm sorry about the minus sign over here, I p dot. So these are the two expressions for the field, almost identical. Difference is that in the second expression x is the 4 space-time vector, while in the first expression x is just a 3-dimensional vector. And this is Heisenberg. You can say we kind of demand this. There are various ways to approach this thing. We start with the Hamiltonian, and then we show that if you do the time evolution of the Schrodinger picture, you will get the Heisenberg picture. Okay, where x naught is the time by which it has been evolved, and p naught is the energy ep. Okay, so that's what it comes over here. Okay, now it's important to ask the question, what are these ap and bp operators? So we work with in both the cases, both in Schrodinger and the Heisenberg picture, we have AP alpha acting on vacuum is equal to 0. Okay, so this is the annihilation operator, and likewise BP alpha acting on 0 is me. So BP dagger is a creation operator, and AP dagger would be the creation operator. So this 0 is the vacuum to which it is annihilated. Now we can ask the one particle state. Okay, so one particle state, let's just say particle. I emphasize on the particle thing. Okay, so a particle with momentum p and spin s, okay, can be obtained by twice EP times A P S dagger acting on y. Okay, so this normalization that I have used, I have taken exactly as you have in the scalar field from the QFT1 course. Okay, all the normalization, everything I'm borrowing from there. So this is my one particle state. So in momentum P, there is and spin S, there is one particle. Now what happens if I want to put another particle in the same state? Okay, so I will act by this operator once more. Okay, and it will be two particle state. Two particles in the momentum, having momentum P and the spin S. Okay, so that would require me to have square root of 2 EP A P S dagger acting twice on vacuum. It should give me two particles in PS state. But I know fermionically it is not possible. Okay, this is, we can just say, not possible for fermions. This comes from our Pauli's exclusion principle. Okay, so what do we do? How do we understand here? So twice EP is just a numeric just a number. What it tells me that A P S dagger square as an operator must be a null operator. Okay, that's one thing. This is something we need to mark. So I need this. Okay, this is one particle state, and this is two particle. Same for antiparticle. Okay, so antiparticle will, using similar argument, I'll get BP S whole square is equal to 0. Okay, now let's look at genuine two particle states. Okay, not two particles in the same state, but two particles with different momenta and spin. Okay, so I want one particle in momentum P, 1 S1 is the spin, and another particle in P2 and S2 spin state. Okay, so I want to create this state over here. So this will be created by, this would require, so how do I write it? I can write it as P1 S1 semicolon P2 S2, and this should give me square root of twice EP1 square root of twice EP2 AP1 S1 dagger AP2 S2 dagger acting on vacuum. Okay, this is my two particles. Okay, so I use the generating, I created the second particle first, and then I created the particle number of 1 later. Now this is the, let's say this is my convention. Okay, so I can say what is my P2S2, and so if I exchange these two particles, okay, this state if I have to create, so that will go as square root of twice EP1 equal to twice EP2 AP2 dagger plus to AP1 S1 dagger acting on vacuum. Okay, but this has to be minus of P1 S1 P2 S2, because if you extend to fermions, the wave function picks up a minus sign. That's what we know from quantum mechanics. Again, a part of Pauli's exclusion principle. So this gives me that AP2 S2 dagger AP1 S1 dagger equal to minus of AP1 S1 dagger AP2 S2 dagger. This is another property I got. So let's look at these three things. I cannot put, using the Pauli's exclusion principle, I cannot put more than one particle in a given momentum and spin state, and two particle state which have different momentum and spin. Either momentum is different or spin is different, or both are different. They must have the overall anti-symmetry under the exchange, so that can be emulated only if these operators that we have anti-commute when the momentas are not same. Okay, so this is what. So and of course there is a certain self-consistency that if I demand that these operators anti-commute, so of course the square of an operator will give me 0. Okay, so what is what are we requiring for at least these three situations that can be satisfied using this thing, that if I have if I have APS dagger, okay, plus AQ R dagger plus AQR dagger APS dagger, this is equal to 0, and this is nothing but the anti-commutator of APS dagger and AQR dagger is the anti-commutator. So the two A daggers with differing anti-commute, and this automatically says that APS square dagger square is 0. So that also is true. So this also implies, using simply the dagger of the whole thing, that APS and AQR anti-commutator is 0, and APS square is 0. Similarly, the anti-commutator of BPS with BQR would be 0, and BPS square is 0, and BP dagger S and BQR dagger, this is also 0, and BPS dagger square, these are all operator level identity, of course. So we also have A and B mixed case. Okay, so there will be APS BQR is equal to 0 with dagger or without. So these are four relations. So you can put dagger at two places, only one place, that's two ways, and no places. So there are four identities are like this. So all of them anti-commute. Okay, so basically all of this AP, S and B, Q, R anticommutator. Okay. What we don't know about is what happens to A, P, S and A, Q, R dagger. Okay, what is this? And B, P, S and B, Q, R, let's say dagger. What is this? This is the only thing we don't know yet. Okay, so let's move on to that. If we recall, the field momentum for Dirac field phi psi is equal to I times psi dagger. Okay, now what usually we need is in classical field theory is the Poisson bracket between coordinate and corresponding momentum, which while I'm quantizing goes into Q hat, P hat, okay, commutator. Now here, if I start from the classical part, what do we have over here? That our coordinates for Dirac case is psi field, momentum is psi dagger field. Okay, so what we have is that something on the left hand side should sit, and on the right hand side, since it's a Poisson bracket, has to be equal to 1 for canonically conjugate quantities. So since it's a continuum quantity, it has to be proportional to the delta function. Okay, so basically this roughly boils down to saying psi of x and psi dagger of x, the Poisson bracket. So let me write PB, not the anticommutator. Poisson bracket PB is proportional to delta, again should be I delta 3 x minus y. Okay, it should be proportional to something like that. Now on the right hand side, the delta function is kind of symmetric. Okay, so here we basically what we need is a quantity which replaces the Poisson bracket with a anticommutator as we have over here. So this particular quantity also has to have correct structure. What I mean over here, that for scalar field or ordinary quantities, it simply went from the Poisson bracket to the commutator, but we know that the psi and psi daggers are made out of anticommuting objects. So even at the field level, okay, what we would require rather is that they should anticommute. Okay, so the correct set of anticommutator would be that I have to write in terms of the components of the psi field. Psi A at x and psi B at y dagger over here. This is anticommutator is equal to delta 3 x vector minus y vector, okay, times delta AB. Usually an I sits over here, but the momentum itself has an I times psi dagger, so that takes care of the I. And all other anticommutator, which is psi A at any x and psi B at y, this must anticommute, and same for the psi A dagger x and psi B dagger, this anticommutator. These things we need. Okay, that in terms of the corresponding the raising and lowering operator, that basically boils down that the two unknown things that we wrote on the previous page is, we can just check. So A, P, and this thing. So A, P, S, and A, Q, R diagonal. This is same as B, P, S, B, P, R diagonal. So both these anticommutators are same, and that is equal to 2 pi Q delta 3 P minus Q, and of course delta. So this is something we will have, that even A's and B's will anti-commute. To see it better, let's look at to emphasize this thing even better, let's look at our Hamiltonian. Okay, so we can construct our Hamiltonian as we have. So here have we written the Hamiltonian? No, today we have not written the Hamiltonian. So let's go for the Hamiltonian expression. From previous day lecture, we know that Hamiltonian density is minus I psi bar gamma I del I psi plus m psi bar psi. And just to remind, psi of x in the Heisenberg picture we will write is T3p by 2 pi q 1 by square root of twice Tp sum over alpha, and you have A P alpha U alpha P exponential minus I P dot x, this is a 4 product, and B P alpha diagonal V alpha P exponential I P dot x, this also 4 product, and likewise psi bar of x from here is T3 P by 2 pi. Or just to make life easier, let me use different symbol over here. T3 Q 2 pi Q 1 by square root of twice EQ sum over beta, again using a different notation for all the dummy variables. AQ beta U beta PQ exponential minus, sorry, this will be plus now. Okay, and here this becomes U bar, and sorry, this becomes diagonal because this is a side diagonal. I P dot x plus B Q alpha V bar, my apologies, we are using beta over here, P Q beta beta Q, and we are using Q here minus I Q dot x. This is the expression. So first thing first, we check what happens to the, we compute this term. This is the, sorry, this is the Hamiltonian density. So my H, total H is G3x of this, G3x times this guy is my total Hamiltonian. So let me look at the term 2. Okay, so I can mark it first. This is my T1, my T2, and I'll separately evaluate them. So let's just look at what is my T2, and that is T3 x, m is sitting outside, T3x times psi bar x psi. Okay, now psi bar x and psi x has this, each one of them has this structure, so there will be a lot of integrals over here. D3x, d3p by 2 pi cube 1 by square root of twice dp, then d3 q by 2 pi cube 1 by square root of twice eq. So these are all the factors that is sitting in front. Then I have summation over alpha and beta, and now let's write down the term one by one, starting from psi bar. Okay, so I also maintain the order of A's and A daggers and B's and B daggers, since these do not compute. In fact, they are anticommutator, so I have to be extremely careful about how they appear over here. Okay, so first term over here is first term would be A Q beta dagger, this multiplying with this guy, so I'll write next to it A P alpha, and what I have is U beta bar Q U alpha, okay, and then exponential of I Q minus P. Okay, this is all terms multiplying first term of psi bar and first term of psi. Now let's continue with the first term of psi bar, the second term of psi. So this will have A Q beta dagger B P alpha dagger U bar beta Q V alpha P exponential I Q plus P x. Okay, okay, I should have point, that's okay. This I should have written actually in the Schrodinger picture, so my apologies here. This doesn't have minus and this has minus, and when I do a complex conjugate, this doesn't have, and this has a minus. That what makes here overall minus. Okay, plus now let's start with the second term in psi bar, which is B Q beta, and the first term of sign, which is A B alpha, and you have V bar beta Q U alpha B exponential I Q plus P x. The last term, which is the last of both of them, is B Q beta and B P alpha dagger V bar beta Q V alpha P exponential I U minus P. Okay, and here the bracket closes. Now here when I perform my x integral, then this becomes delta 3 with a factor of 2 pi q. So this becomes 2 pi q delta 3 p minus q. Same thing happens here. Last term 2 pi q delta 3 p minus q, because it's a 3-dimensional integration. And these two terms, yellow is good enough, these things will go to 2 pi q delta 3 p plus q. Okay, so after having done the x integral, I get this exponential factor converted into these delta functions. Then I perform you cancel the 2 pi cube with the 2 pi cube over there. So let me use a different color. So this 2 pi cube and all set of these 2 pi cubes cancels with this 2 pi cube. Then you perform the integral of the q. Then in some of the terms p becomes equal to q, in some of the terms p become opposite of q. But in both the cases, since we have this E of p vector is equal to E of minus p vector, which is equal to just EP, so energy will be exactly same. So what I'll get over here after performing the q integral and the x integral, my T2 would be m times d3 p by 2 pi cube. That will be for sure. And then 1 by square root of, sorry, there is no more square root, just twice EP. Okay, need to be just twice EP. These two guys became same. And then I have certain identities to use. So maybe that I can write in think. So what are these guys? U alpha and U beta. U bar alpha and U bar beta. Okay, when P is equal to Q. Okay, that's very important. Now P has become equal to Q, or maybe I should write that once. So let's come back to thing. So I can start with summation over alpha and beta. A, and now P and Q are equal, so I can just write P beta dagger A P alpha U bar beta Q. Sorry, this has become P now. U P. Okay, alpha over here plus A. Q has become minus P over here, minus P beta dagger B P alpha dagger U bar beta minus P V alpha P is a term. A similar term over here, B minus P beta AP alpha V bar beta minus P U alpha P plus apologies, BP. Here it is, the sign is same, so BP beta BP alpha dagger, and here term is V bar beta P V alpha. This is the term. Okay, so now there might be some carefully copy to the next page, but before that we just say that what we are going to use is some normalization conditions, not a new normalization condition. So again, so the normalization conditions are going to be u bar p vector. Let me write the p vector alpha, since I was using beta as a function, let me write beta u alpha p is equal to twice m delta alpha beta. Okay, and v bar beta p u, sorry, v again, v alpha p is equal to minus 2m delta alpha beta, and other two terms, u bar beta with minus p and v alpha with p is equal to 0. And this is, you can check with when the three momenta are equal and opposite, they actually satisfy orthogonality condition. This is a very special case. This I haven't shown in the class, but this can be checked. And v bar beta minus p u alpha p is equal to 0. Just want to emphasize these two terms I have not shown to you, but these are important relations. Now from here we look at this. So what happens that this guy becomes plus 2m, this guy becomes minus 2m, and these two central pieces, mixing pieces, becomes 0. So what I have for my T2, my T2 is m, and I still have my D3P, I guess. So I have my D3P by 2 pi cube 1 by twice EP. Okay, and I have summation over alpha and beta, and first term is a, and since there is delta alpha beta, let's say eliminate okay, so let's eliminate alpha, sorry, let's eliminate beta by summing over alpha and beta. So I have a p alpha dagger a p alpha minus b p alpha b p alpha dagger times twice m. Okay, this is the important thing. So this is multiplying with a factor twice m, and I can take this term to be this m inside. So I have d3p by 2 pi cube, and 2 cancels out, so I have m square by ep factor, and then sum over alpha, and this is change factor a p alpha dagger a p alpha minus b p alpha b p alpha dagger. This sits over there as my term, second term. Okay, my second term. Now I have to compute the first term. So first term, to compute the first term, if you see, I first need derivative of psi. Okay, minus I times derivative of psi, and these are only the three components. So as you can see, if you just put derivatives to xi's, then you basically get I times p. Okay, and minus I is sitting over there. So what you end up getting for derivative is a simple expression if I have psi expression given by that, then del I of psi x is T3 p by 2 pi q 1 by square root of price EP summation over alpha, and you have A P alpha U alpha T, and then you have PI. So I have to say minus I times del I am taking PI exponential, here it is, since it's spreading a picture, I P dot x minus, here the sign becomes minus because, or maybe I should say plus, B P alpha dagger V alpha P, then I have minus PI exponential minus I P dot x. Okay. This minus comes because here the P has opposite sign. Okay, so this is first thing to note, and then second thing we will have is the use of okay, so this guy has to multiply with gamma, so let me also multiply it by gamma I over here. So I will multiply here with gamma I, and here I will also multiply, so let me erasing minus gamma I Pi. And did I made a mistake? Big mistake. Gamma is to the left and the spinner is to the right. Okay, so this thing that is gamma I Pi U alpha of P, and here minus gamma I Pi V alpha of P. Okay, so gamma is multiplying from the left hand side. Now to this, okay, this is one term in the Hamiltonian, part of the one term, so I just minus I times gamma I del I psi I wrote, and that has to be multiplied by psi bar. So my T1 is T3x, okay, psi bar of x, which has to be multiplying minus I gamma I del I psi of x. Okay, this is what I have to multiply. So the second term is written over here, and the first term is written in the previous slide. Okay, but before I jump any further, I need to make certain simplification, which is maybe I will move this guy below. Okay, this is what I have to write in the term, and but from the Dirac equation, what I know is my gamma mu P mu acting on U alpha of P was equal to M times U alpha of P. Okay, so once we have this relation, I can also write this guy as gamma 0 P0, okay, is equal to minus, on the other side, gamma I Pi gamma I Pi plus M. What did I do? Yeah, it's I would like to just break it into the I part and the P part. So here I'll write IP. So gamma I Pi acting on U alpha of P would be gamma 0 P0 minus M Okay, and this will simplify u alpha of p. So here M has just identity matrix in front of it, and gamma 0 is also simpler to handle. Okay, so here we will move on to another expression, some other normalization condition. Like here we have bunch of normalization condition. So here some other normalization condition that pop up involves not u but u Dirac. Okay, so what are we looking over there for is okay, let's come to the next page. So we can see over here that this gamma IPI is acting on u of p is can be written like gamma 0 p0, which is same as the energy minus m. And similarly, just before going to the next page, I can see that gamma minus gamma I vi acting on v of alpha of p can be written as gamma 0 p0 plus m v of alpha of p in a similar manner. Okay, and again the benefit of replacing gamma i's with gamma 0 is that with gamma 0 I can still convert the u bars and v bars back into u Diracs, and there we need a separate set of relations for the next for this term. So as you can see, my T1 is here. So T1 is a product of this guy, what we are going to write, and psi bar, which we have already written. So, and again, what we need is that they will have 4 terms, and we can already say that certain expressions will be there. So we will have expressions like say u bar, beta p, and then I will have gamma 0 p0 minus m times identity, and u alpha p, and we have to figure out what this quantity would be. So here what I will need is 2 terms. As you can see, is gamma 0 times u bar will become just u Dirac. So we'll have u Dirac beta of p, this is multiplied by p0, and u alpha of p minus m times u bar beta of p u alpha of p. So this thing is twice m, we know. Now what one needs is what this kind of relationship is. Okay, so this is what I would like to write over here in this, is that u Dirac beta of p u alpha of p is equal to twice m, I'm sorry, there is no m, twice e delta alpha beta e of p. Okay, which is same as p0. Okay, so this is the relation, and this was the quantity as we discussed earlier, that it was not Lorentz invariant because energy is not Lorentz invariant. So and usually this is what appears when we write down the density, the 0th component of the 4 density 4 current. So the density will scale up like energy. And similarly, we have v Dirac beta p v alpha p, and that is also twice ep delta alpha beta, mind there is no minus sign. Okay, so this is the thing. And additionally, very important, u Dirac alpha of p and v beta of minus p, this is 0, and v Dirac alpha of p u beta of minus p is 0. So this is another set of special identities, you can say. There's a specific property for these guys. Ideally, there is no reason why this 2 has to be 0, but when the momenta are equal and opposite, then there is a special property that this u and v also are orthogonal, okay, at the diagonal level as well. So this is these are a set of relations that we are going to use. And here again we want to say that because of this mixed condition being 0, the only non-zero component that comes is u with u and v with v, okay. And of course we have done the to arrive at that quantity, we have done this three-dimensional integration of x, and here p and q are there, then some of the integration of q is done, okay. So I am only left with the integration of p. So I'm writing my d1 to be d3p by 2 pi cube 1 by twice ep. This is what we have, and then we have this summation over alpha beta, okay. The term with u, as you can see over here, u beta with u dagger. Here what did we have? If we use this piece twice ep, okay, and twice m over here, and p0 is ep, and I have here twice ep square, okay. This quantity is twice ep times delta alpha beta, and here is 2m minus twice m square delta alpha beta. Now what is this? This is nothing but twice p square delta alpha beta, where p is nothing but the momentum, okay. So what I'm going to write over here is a p alpha, and let's say let's assume that beta summation is also done. So ap alpha dagger ap alpha is multiplying my twice p square, okay. So let me write twice p square outside, or let's multiply here 2p square, okay. But in the second case with v's, okay, you saw there was already a minus sign in the v, okay. So what we have here is minus on the left and minus on the right. So for the case of v's, okay, I can write it over here. So I have minus gamma I pi acting on v, let's say alpha of p, and here let's say v bar beta of p will come. So this set became, so here v bar beta of p, the minus sign, because of this minus sign will be there, gamma 0 ep plus m, okay, v alpha. Now here what happens, the minus sign remains outside, v bar becomes v dagger with ep. So I have v dagger beta v alpha multiplied with ep plus m, and v bar beta v alpha. And as we see from this normalization condition, this thing here, let me write minus sign outside. First term becomes ep square times delta alpha beta, second term becomes 2 times minus 2 m square, because v normalization is negative, delta alpha beta, and that becomes minus p square delta alpha beta, okay. When I put over here, so it becomes minus bp alpha bp alpha dagger twice p square, okay. This is my term 2 will become. If I combine term 1 and term 2, what we'll get is what we are getting is t1 plus t2 is nothing but d3p by 2 pi cube. Here again 2 cancels out, so I have p square by m, and there we had m m square by 2, sorry, p square by ep is there. So I have basically, let me write p square plus m square by AP sum over alpha AP dagger AP alpha minus BP alpha BP alpha dagger. Okay, so this guy is nothing but AP. I'm not repeating the term. Okay, so this is nothing but my Hamiltonian. So let me just finally write Hamiltonian is D3 P by 2 pi Q EP sum over alpha of A P alpha dagger A P minus B P alpha B P alpha dagger. Now, the second piece is coming with a negative sign, but we have already agreed that it is B P alpha which annihilates the vacuum and A P alpha that annihilates the vacuum. So in a way it's okay, not an issue. The first term just looks like the standard oscillator. The second term doesn't look like the oscillator, but we have already in previous slide we have argued that I want the anticommutator, okay, between these two guys to be something non-zero. Okay, so if I use that anticommutator, okay, and swap these things, so what will happen between these two? They are same momentum and same spin, and when I do the anti-commutation, a delta function will come up and the sign will change. So this will become D3 P by 2 pi Q EP sum over alpha AP alpha dagger AP plus BP alpha dagger BP alpha and plus huge constant. Okay, integrated multiplied by AP integrated over D3P, but we throw that part away and we call this guy to be our, basically this is the excitations above the infinite energy shift that we have considered over here constant. So this is our Hamiltonian. Now important thing to note over here is that A dagger P alpha creates a state of particles that we say represented by the spinner U. The wave function of that guy is spinner U, and that is a positive energy, because here you can see E is positive, is a positive energy state and positive with the given momentum. You provide the momentum and then you ask what is the energy. So P is arranged according to the P, and same is happening with the B operator. So with this antiparticle are not really the negative energy states. That's the way we have chosen the convention of A and B daggers, A's and B's, is that the existence of an antiparticle above the vacuum is also a positive energy solution. That we have to provide energy to create an antiparticle, like the way we require it to create a particle. Okay, so these are the energetic one has chosen, the conventions one have chosen, and this kind of keeps that kind of kills the negative energy issues that one had in our Dirac theory. And this is bit involved. I'm jumping some of the steps over here. I'm directly giving you the answer in terms of anticommutator. The key thing is to use the anticommutator. Okay, and usually what people do, especially in the book of Peskin, what is done is that you first start with commutations, and then you say that there is issues with the energy stability. Then to make the energy stable, you have to postulate the anticommutation, and then you show that for fermions where this negative energy solutions were there, to cure it we need to introduce anticommutation, and that naturally gives the fermionic nature of the particle. Here in this discussion we are doing it other way around. We are focusing on the fermionic nature of the particles, and hence concluding that the anticommutator is the right way to do it. And then at the end we are showing that the antiparticles, so are the particles represented by the wave function spinner V are actually the positive energy excitation in this way of writing. So if we use anticommutator, it will take care and make it sure that it is a positive and negative solutions. This is a very important fact that we have to keep. With this, we conclude this lecture. This was the first attempt on recording the lectures. There were some errors, so this is roughly full time because I made mistakes. I corrected it, and I'm not editing those videos, those part of videos away when I made the mistakes. Hopefully from next time when I learn about the editing bit better, I will remove those things, so that will save you a lot of time, because you won't be going through the parts where I'm writing and erasing. So you will only have the parts where the right thing is written and all the pieces of discussions are there appropriate. So next lecture should be better than this. This was my first attempt. See you in the next lecture.